And if you have any questions, then please ask it by typing. Everybody except instructor is muted. Use the questions window. All right. So please be clear in your question, and uh, because it takes me some time to figure out a meaning. All right. Let me mute my phone. Done. So this is session number 1 out of 11 sessions, and yeah. So about no big data, we take proud in saying that we have great set of instructors, and we have something called CloudX Lab, where everything will be available to you online. You don't have to install anything, and there'll be a lifetime access to learning management system. Whatever presentations, recordings, assignment, and quizzes will be available to you forever, and all of this will be available in LMS. So Dosi's question is how soon the recording will be available in case I miss the class. So it takes around 2 to 3 hours after the class. Okay. Now we provide you with a real life project if you finish our normal usual project work, and we provide the course completion certificate. Along with that, we have 24 by 7 email support. And we have a good group of people as alumni, and we keep a connect with all of them in with respect to the jobs, with respect to the newer updates to the course, and we stay connected as an alumni of No Big Data. All right. So let me go through your introductions quickly. So we have Hiran Doshi, we have Mehndi Hassan. Mehndi Hassan is okay. He's working as Informatica ETL dev. His current project needs some knowledge in Hadoop and Spark. Last week he finished Cloudera CCA 500 exam and installed Namenode on 2 CentOS machine and Datanode on 4 CentOS machine. I need Spark on one of the machines. All right, all right. So Mehdi, no problem, no problem. So if you drop me an email, I can help you out setting the Spark quickly on one of the nodes. All right, good. We have. I'm really happy to have you in the session, Mehdi, and you can also you can also help other people a little bit about the who are aspiring to take Cloudera certificate. Great to have you in the session, and would love to hear you on one-on-one. All right, we have Hiran Doshi signing from Toronto, Canada, and is working as independent consultant. He has taken courses on Hadoop development and did Cloudera Hadoop certification. And wow, so we have Hiran Doshi who has also a Cloudera Hadoop certification. Great, great. All right. Are you able to hear is everybody able to hear clearly? Great, great, Jitendra. Now you can hear. All right. We have Harsa, who is working as big data development and admin in Mercedes-Benz in R&D. Great to have you in the session, Harsa. We have George from Bangalore. Great, George DeCosta. And all right. Prabhakar's question is, does big data certification provide by any enterprise which is widely accepted? So, Prabhakar, there are two, three companies who provide the big data certificate. I mean, Hadoop certification. One is Cloudera, other is Hortonworks, and other is MapR. Okay, so for some companies, certification do matter, but yeah, but focus on the learning more, right? Harsha is looking for a career in Spark and is a Cloudera certified developer. Wow, we have three people in a single session with a Cloudera certified. Good, good, good to have you in the session. All right. So we have Prabha who is working as Selenium test engineer and would like to move to big data. Good, good. He's from Bangalore. Okay, okay. So Hiran Dosani. Okay. Did I pronounce your wrong name? All right, all right. We have Jitender, who is working as data solution architect, currently doing design for big data, Teradata, and everything else. Brilliant, brilliant. So we have a great, great set of users today. Great. All right. So before we start, do you have any questions for me, or should I start? All right, no questions? Good, good. So Jitendra is saying that he wants to really get into big data architect and defining data pipes capacity, etc. Good. All right. So about myself, you must have gone through my profile as well. So I did my graduation from in 2002. That was far back, and from IT Roorkee. Then I worked at a company called DE Shaw, where we had built our own big data systems uh, 13 years ago, meaning we were churning terabytes of data when people were not even aware about it. All right. So that was the time where we were having a 10,000 node cluster. Afterwards, I started a company called Tvits Global, where we built a document management system for large enterprises. And then we started a company. I joined in Mobi and built a recommender churning around 200 terabytes of data. Afterwards, I worked with Amazon and helped them improve their Amazon the detail page of Amazon.com. The detail page is the one where you have the big image on the left hand side and you have the details of the product, and from there you make the purchase. So we built high throughput systems for Amazon.com's website. For basically, we improved the image which is displayed on the left hand side, and for that I built our own stream processing system similar to what you have Apache Storm. Now this is stream processing system is being used by multiple teams in Amazon now. So that's what I worked on at Amazon. All right. So that was brief about myself. So I hope this term does not need much of introduction. So, so what exactly is big data as per your understanding? Yes, anyone? Just give me a brief about what do you understand by big data. Yes. So, what is your understanding of big data? All right. So, Jitendra says that it's a very large and dynamic unstructured, while Mehndi says it's a concept, and Harsha says high volume of data and is a concept. Good. Mehndi says it's a HDFS and MapReduce. All right. Good. Good. So we will keep ourselves very clear to I mean very we will have our definition very clear, and we will just keep this definition in the following manner. So, data of very big size. So, whenever we say big data, it means data of very big size that you cannot process with your usual tools, and you generally require distributed architecture. And the data could be in any form, whether structured or unstructured. So, distributed architecture needed. This is the definition which we are going to be with. Okay. The third point is the most important point out on this slide. So the way we will be classifying big data is any data, whether by virtue of its volume, velocity, or its the problem statement or the complexity of data. If we require distributed architecture, then we call it big data. All right. And what do we mean by distributed architecture? It means group of networked computer interact with each other to solve a common problem, to achieve a common goal. Okay? So you connect all these computers together and utilize all of these computers simultaneously to solve your problem. Alright? Be it Hadoop, be it Spark, be it any of these components which come under big data components, they all have one thing common, and that is distributed computing support. So all of these components, whatever we discuss under big data, they all work on multiple computers simultaneously. All right. All right. The one benefit of distributed computing is that we utilize so many computers parallelly, and meaning that you have got so much of RAM if you combine all of these computers, memory and CPU and hard disk read speed. The other benefit of distributed computing that they need to exploit is that we take the code to the data. Okay, meaning if the code is X and the data is wood, then we are basically taking the X to the wood instead of carrying the wood around to bring it to the X. Okay, so generally the code is far smaller than the data, and therefore it makes practical sense to transfer the code rather than rather than transferring the data. All right, and that is why in almost, whether it's Spark, whether it's MapReduce, everywhere we send the code. We we create these functions, we create these handlers, hand over it to the platform along with reference to the data, and let the platform solve our problem. So that is how most of these distributed computing products work. All right. I'll be discussing a bit about volume, velocity, and variety, and the use of and the corresponding components from Spark that handle it. So the volume, which is data at rest, velocity, data in motion, and variety, that is data in many form. So the last point is something which I would emphasize more, the variety part. So when we say variety, it's not only the variety of the data structure. It's not only the variety of data. It's also the variety of problems that you're trying to solve. Okay, let's take a simple case. So first two, I think everybody is aware about. If not, let me just describe it once more. So volume is when your data is becoming bigger and bigger, your storage is the problem. Then we say that our data is big because of its volume. We are not able to store our data because of its size. Then we say that our big data is big data because of the volume. Okay, so whether you are trying to store the logs of a website, or maybe you are building a system like Gmail where you're storing lot of data, then your first problem that you hit is the volume. Okay, second is the velocity. So your big data might become big data because it has got the velocity, or in very simple words, your problem might require distributed computing because of either of these three characteristics, be it volume, be it velocity, be it variety. Okay, so the velocity part is a problem involving the handling of data that is coming at a very fast pace. Okay, be it you want to display the current keyword being discussed on Twitter, or the current trends in a stock market. Everywhere the velocity is a problem. Now, if in case you are handling such a fast stream of data from a single computer, you may not be able to handle all the requests. Okay, the other way to look at velocity is when you are refreshing whenever you log into Facebook, there's a request going to the server at the same time, right? Now, this request, if you think about all the users of Facebook, and think about mobiles and the desktop, total number of requests that are going to Facebook are in millions per second. Now, millions of requests cannot be handled by one node, cannot be handled by one single computer. Therefore, Therefore, it makes sense to distribute these incoming flow of requests to multiple machines. And that's what we call the velocity part. All right. Now, the third one is something which is very interesting and something which comes when you are able to solve volume and velocity problems. If you are able to solve a volume or velocity problem, the next is handling variety of data. Okay. Now imagine this. You have got say say 1,000 models of car. Let's say there are 1,000 models of cars. And so if you think about it, so 1,000 models is not a big volume. Now out of these 1,000 volumes, all you require is find out find out the the classification hierarchy, as in, out of these 1,000 cars, which cars are closer to each other, which cars are far distant from each other, and so on. All right. So you have to classify the way Darwin helped in classification of animal hierarchy, as in the humans and monkeys are very similar to each other, and so on, right? Mammals. So if you have to prepare that automatically and you have characteristics of all the animals together, it takes a very much amount of computing capabilities, right? Because you have to do so many permutations, you have to do a lot of work. Similarly, if you have to traverse a social graph or any of the problems like searching in the map. These problems are complex. Okay. So all of these problems come under variety. Okay. So even though there is no volume, I mean very small volume of the data, and there is a small velocity, there is not, you are not needing the something per second basis. Still, because of the variety of problems and variety of data, you would end up having distributed computing. All right. Did it make sense to you? Is everybody clear about volume, velocity, and variety? All right. So I wanted to emphasize more upon variety part because that's where Spark has done a really marvelous job along with velocity. Okay. So the Spark streaming specifically handles the velocity part, though Spark doesn't handle volume, but Spark streaming handles the velocity part as well as your normal transformation and action. We will talk about transformation and action of Spark later. The velocity is very important aspect. Okay, velocity is something Spark is able to solve. All right. Next is variety. So Spark has done a really great job. The team at Spark and the open source community has done a marvelous job when it comes to variety, meaning solving really complex problems, solving really complex problem and at a very fast rate. So Spark has provided something which other platforms have not provided yet. The platforms such as MLlib, machine learning library, and Spark has come up with Spark ML kind of a language. And Spark also provides you the GraphX library for processing the graphs and they have done something really, really marvelous, which nobody else has been able to do. They have ported R. R has been ported to Spark R, because R was the earlier machine learning library having tremendous amount of code available, having tremendous amount of functions available in for machine learning. Okay, so Spark team and Spark open source community has made it possible to run the packages of the R in Spark R, which means you will be able to run any package of R inside Spark. And what does it mean to us? While normal R used to run on a desktop or a laptop, right? And it could not scale beyond what could fit into the memory of that computer or that laptop. Okay, so if so since R was not able to scale up, could not go beyond one computer's memory, therefore R was heavily limited. Okay, because most of the complex machine learning problems requires a lot of memory and the computing. Therefore, being able to do the same thing what we did in R without in a change in a code is a big boon to the whole machine learning, to the whole machine learning community, because now you will be able to do the distributed computing and solve your complex problem which you could not do using R. Sounds good to you? So MLlib, GraphX, Spark SQL. Spark SQL is not a really good example here, but Spark R is important aspect. Okay. All right. So this one everybody knows about it, I think. So how many bytes are there in petabyte? Quickly, this first answer, and I'll move. It's just to see if you are there or not. All right. Anyone? How many bytes are there in 1 petabyte? John says it's 1024 in 2024 in 2024 in 2024, which is 4 into 3, which is okay. So, are you sure, John? All right. All right. Anybody else? Correct. Thank you, Harsha. It is 10 to the power 15, and yes. All right. Ishwar has written so many zeros that I can't read them. Two, two, two. 2 plus 4, 6, 8, 10, 12. So, alright. So it's 10 to the power 15, and a quicker way to remember it is that 1 petabyte has 1024 terabytes, and 1024 terabytes has 1024 gigabytes. And gigabytes has 9 zeros, so terabytes has 12 zeros, and petabyte has 15 zeros. Alright? So what is important is how many zeros it has. Alright? Because whenever you have to do a quick computation that this much data are we getting, you should be able to just use a back of the envelope kind of model and should be able to estimate that that should be able to quickly estimate that what does it mean, what does this particular big data mean for your with respect to your architecture. Alright? Alright. So why is it important now? So, I mean, since the big data has become a commonplace, as in every company who is having decent amount of traffic will have a decent amount of data. So, having such big data tools has become very important because data is being gathered by various means and is happening really fast. Now, why did it start happening? Because first is because of the hardware. The mobile phones kind of devices became so popular and became so handy, as in the three criterias which any hardware manufacturer keeps are cheaper, faster, and smaller. Every hardware manufacturer, specifically the mobile devices, they had been trying to build cheaper, faster, and smaller device. And smartphones are their success so far. So while on one hand, the smartphones which have so many sensors, so I mean they can take users can take pictures, you can do a lot with smartphones. So on one hand, when we have so many devices connected to internet, and and on other hand we have the connectivity. So devices and connectivity coupled with software has led to a lot of data, which is something users can use, people can use to derive meaningful insights. All right. So the reason why it's important right now is because we have so many devices which are connected well together and producing data. Okay. And that's why to churn that kind of data you require really large systems. All right. Quick question to everyone. Which components impact the speed of computing? Out of these, A to G. All right, all right. So everyone says that the the components that impact the speed are all of above. Yes, that's correct, Hiran. That's correct, John, Mehndi, and Svar, and Harsha. Brilliant, brilliant. So disk size also impacts the computing because if your disk size is small and data is little bigger, you will try to move it to the network. Okay, I'm trying to answer Mehdi's question that not E. Yes, you're right. So because sometimes we think that disk size does not impact the speed of computing, but it does. If your disk is smaller, then what happens is that you move some data to the network and it suddenly becomes slower. All right. Brilliant. Now there is a question from Ishwar. Does Spark support real-time streaming, offline streaming? So this Spark supports real-time stream processing. All right. We will discuss it in detail again. What does it mean, and how do people use Spark to handle the large stream of data? Make sense to you? All right, all right. There are many customers to big data, starting with web and e-commerce. All right. So the most common use for the big data is the web and e-commerce. It could be recommendation engines, it could be analytics, it could be predicting the demand in case of e-commerce and web. So analytics is of many kinds. Starting with your normal analytics, where we are observing the behavior of the users, we are noting it down. Other is A/B analytics, a kind of A/B analysis, whereby we display some variation of a component to some set of users and some other variation of components to other set of users, and measuring the success of each component, and measuring which version of the component need to be kept. So analytics is again a big data problem when it comes, when we try to solve it. All right. So in web and e-commerce, it's very obvious to have these recommendation engines, analytics, and predicting demand, as well as in case of web and e-commerce, storage itself becomes a problem. Okay, storage itself becomes a big data problem. All right. Next is the telecommunications. The telecom companies, they can prevent the customers from leaving their network if they are able to predict why are the customers leaving them, right? And the way they can do is, if they can correlate the data, if they can do the analysis quickly on how many calls did the customer made to the support, as well as how many, what was the signal strengths at various period of time. Along with that, along with that, mm, for how much data, for how much time his phone was in the uh, in the connect was online. And so if telecom companies are able to predict that, then they can prevent the customer leaving them. Next is network performance optimization. So these are few use cases with respect to telecom companies. So they can improve their network by load balancing the capacities based on predicting the load. As in if they are able to predict that these many users will be in the business park at this particular time, and therefore I mean, if they are able to predict the population movement in a city, then they should be able to predict they should be able to handle the network performance. Accordingly, they will do the load balancing. All right. Then calling data record analysis. So that is another use case of big data. Okay. As in figuring out, based on the calling data, figuring out various correlations, figuring out even the even the terrorist threat from the calling records, and analyzing network to predict failure. That is another part which is very important with respect to the big data. All right. So with respect to recommendations, there has been a lots and lots of work that has been done in case of recommendation. It all started long back. I mean, the problem of recommendation is really old. It's very difficult to trace it back. But recommendation was converted into sales, as in the biggest correlation between recommendation and money was at Amazon, where they realized that the recommendations drive maximum amount of traffic and hence sales. and that's where that's why Amazon has put a lot of efforts into recommendation. Okay, so and similarly there are lots of other companies starting with Netflix and IMDb, and lots of many companies do the recommendations, and recommendation has become really a common problem. Okay, so a recommendation could be as simple as customers who bought this also bought that, or wear this with that, or it could be far more personal. Based on your history, these are the recommendations. Okay, so you can see that these are the recommendations from IMDb and Netflix. Alright, that is the recommendation kind of problem. There are many algorithms which do this. Recommendations is big data problem because of variety, because of the complexity of algorithms. So if you look at it, you have characteristics of the products, you have characteristics of the users. You have to find out which products are similar, which users are similar, and based on this kind of behavior, what is it that once you have figured out which products are similar, you will figure out which users are similar, and based on that you will bucket the users into together, and then you will start giving the recommendations to each other. So this is just one form of algorithm. There are many ways to produce recommendations, and if you think about this algorithm, it is really complex in terms of computing. The big O notation, the complexity, the number of cycles, CPU cycles it will take to compute recommendations are really high. Therefore therefore recommendation is problems like recommendations are generally considered the variety kind of problems. All right, so that's about the recommendations. Next is sentiment analysis. Sentiment analysis is also quite a common problem, as in given the Twitter data, figure out whether we are trending or not, or correlate all the data from Twitter, Facebook, and all other ways and represent that in a graph. Okay, so the first problem occurs when you try to use the Twitter to do the sentiment analysis, and since it's a text-based system, as in people are just typing tweets, ability to figure out what are people talking about, whether they are talking about negative or positive, is something really difficult. Okay, it could be done in a very rudimentary way as well, where we use just count the polarity of each word in the tweet, meaning whether whether bad is negative or bad is positive, or average, when some people say that it's not good, it should be considered negative. So that's just basically combine building a big dictionary of words and marking them negative and positive, and then out of Twitter figuring out each sentence based on summation of these polarities of each word in the tweet. So one way is just do the sort of negative positive things. Other is do the language processing. That is something far more complex, as in just the way human understand the language, use the language processing libraries to analyze the tweets. That is something really difficult, and people are able to successfully do it as of today. Okay, so some of the sentiment analysis is done using statistical techniques, while some of it happens using the machine learning and I mean the natural language processing way. Okay, so sentiment analysis is done in number of ways and is one of the big data problems which is most frequent. All right, other big data customers are the governments and the healthcare. All right, The governments and the healthcare. Government might use the big data and these kind of problems to do the fraud detection, cybersecurity, welfare, and justice, while healthcare and life sciences systems can use the big data systems for information exchange and gene sequencing and healthcare improvement and drug safety. All right. All right. Now, S- I'm assuming that you must have gone through a basics of Hadoop sometime, but I'll just give a quick refresher. So we talked about problem statement so far, the big data problem so far, and why do we need it? Why do we use it? Let's talk about how is that problem solved. Problem the storage problem. The volume part, when we talked about those three V's, the volume part, where our main problem was to store petabytes of data. Okay, so that kind of problem is solved by HDFS by using in HDFS by using many computers or many hard disks on many computers connected over the network to provide scalable and fault tolerant and simple storage. Okay, so that is the role of HDFS. HDFS provides you a very decent amount of storage. It provides you a big folder, single folder structure without you having to worry about managing your data in many files and taking backup of it. All right. So HDFS provides you this kind of a solution. So that's solving your volume problem. All right. So we talked about three things: volume, velocity, and variety. Okay. So So the volume problem, the storage problem is very well solved by systems like HDFS, Cassandra, MongoDB, and many more. All right. So, all right. Now, in case of other computation, so earlier we stored data in HDFS. All right. As usual, we stored data in HDFS and we used MapReduce to do our computation. Any computation we want to do on this volume of data, we used to use, we had been using Hadoop MapReduce. Alright, so there is a user who writes his MapReduce, submits it to the MapReduce framework, and it gets executed. And basically MapReduce as well as HDFS, both of them are running on whole set of computers, not on one. So what we are trying to distribute here, what we are trying to display here is that in case of MapReduce logic, we read and write data from HDFS. Okay, we read data, we take the input of data from HDFS and we write back into HDFS. All right, those who have gone through our Hadoop and MapReduce session, they must know that the user, when basically at the end of all the MapReduce process, they interact with HDFS. So what you can understand from this diagram is that the MapReduce is bound by the performance of the hard disk and performance of the HDFS, right? Therefore, therefore, if you see that if you have multiple phases of MapReduce, so every time the multiple you launch a process, the data is read from HDFS, written to HDFS, again read from HDFS and written to HDFS. That is why there is a lot of latency, meaning it takes a lot of time to execute your MapReduce code, right? Although it's heavily resilient, as in there is a sort of a guarantee that it will get done and even if there is a low memory on the machines, still it will get done. So there is a sort of a guarantee, kind of, heavy resilience, or the sort of peace of mind that it will get executed. But it takes a long time to get work done on MapReduce. All right, is this diagram clear? Are these two diagrams clear to you? So I'm trying to give you a quick overview so that you can understand why do we require Spark and able to appreciate the difference in the architectures. All right. Arvind, Ashish, Ishwar, George, Harsh, Hiran, Jitender, John, Karthik. So everybody okay with this? Awesome. So looks like everybody is there. Great, great. Yeah, we have great set of audience. All right. So all I'm trying to explain is that in case of MapReduce, we interacted a lot with the disk, with the network, and therefore there was always a latency. Typically, a MapReduce job might take up to 15. It might go up to 15 minutes. All right. So there was a heavy latency, even if so it was very difficult to get things done really, really fast. All right, that's where the newer framework was born. All right, so our MapReduce in case of Hadoop was batch-wise design, as in every MapReduce cycle reads from and writes to HDFS, heavy latency. Also, there was one more aspect which we will understand as going forward. So if you're storing something into file system, converting that again back into object for the next cycle is a difficult problem. So every time you have to serialize and deserialize. So the output of first phase here, when it has been written into HDFS. When you are reading it into second phase, again you have to load from the file system, convert it into objects, and process it. So there is a huge overhead of serializing. Serializing means converting your objects or data into a serial form, like I mean that can be stored directly into the disk. Okay, so batch-wise design suffers from heavy latency. Latency means slow, sloppiness, as in it takes time to give the response. Second is converting logic into MapReduce paradigm was fairly difficult. And no, and always, every time you always felt that maybe this particular logic cannot be converted into MapReduce. So it was, even for experienced developers, converting a logic into MapReduce is a difficult problem. All right. The third problem with respect to MapReduce was that in-memory computing was not possible. Okay, in-memory computing was not possible. Okay. Also, you should see this diagram here. I mean, the way you can visualize Spark is that if the MapReduce phase read it from RAM and wrote back to the RAM, then second MapReduce phase read from the RAM and wrote back to the RAM. So in this manner, the speed will be more than 80 times faster because you are reading writing into the RAM. And in case you are wondering how much time it generally takes to read from various disks, have a look at this structure. Okay, you can see that data which is being read from the disk is around 80 times slower than the memory. All right, this is a good GitHub project. You can have a look at it. All right, and this basically tells you the various forms of latency which people have computed. All right. All right, so everybody with me? Great, great. All right, that's where the role of Spark comes into play. That's where the role of Spark comes into play. So also in case of earlier, even if MapReduce starts providing us the memory-based computation, again the paradigm has to be changed. Okay, so therefore sometimes it's required to run the job with a heavy latency, though it might take a little bit time. So sometimes MapReduce jobs are better than the Spark ones, the memory ones. Sometimes the RAM ones are better. All right. So that's where the role of Spark comes into play. So is everybody clear that why do you require Spark? Spark basically does the in-memory computing. Okay. While MapReduce does the computing for with respect to the, I mean, reading and writing from the disk and HDFS continuously. Okay. So Apache Spark is really fast MapReduce. It's 100 times faster than Hadoop MapReduce in the memory. It's 10 times faster on the disk. It's built on the similar paradigm as MapReduce and is integrated with Hadoop. All right. Okay. So the Spark core is basically a fast and general engine, not search engine, a engine for large scale data processing. All right. We'll build upon this Spark core and we'll show you each and every ecosystem on which it relies upon. All right. So while on one hand the MapReduce was great at getting the job done, but it was slow. It was slow because it was writing to the disk. On the other hand, Apache Spark does not read write from the disk unless explicitly required. Okay, unless you say it to the write to the disk, only then it will write to the disk. Otherwise, it will partially read the data into the memory, and also it works in the similar model, as in it loads partial amount of data into the memory. That's up to you. Iswar says, what do you mean by integrated with Hadoop? It means, so everybody, keep that in mind. Spark is not a competitor to the Hadoop. It's just a competitor to MapReduce. That too, fulfilling different kind of requirement. While MapReduce is for reliable computation, far more reliable computation, Spark is for instant computation. Now, Iswar's question is the how is it integrated? Integrated as in it can read from HDFS. It runs on yarn. You will see that next. All right. So the Spark core runs on Hadoop yarn. It can runs almost all popular cluster managers. Okay, cluster resource managers. Okay, not cluster provisioning tools. Cluster provisioning tools are different from cluster resource managers. So, Spark Core can run on Hadoop Yarn, Amazon's EC2, standalone, as well as on Mesos. Yes, Iswar. So, Iswar's question is, can Spark have capability to handle streams of data coming to nodes? Yes. Okay. So you will see it further. We'll take a couple of examples. All right. So Spark Core is running on top of Yarn, EC2, or standalone and Mesos. Standalone, you do not run in production. Instead, you run it only in case of testing. All right. Now, Spark Core can read from many sources. It can read data from HDFS, and it can also take care of the data locality in case of HDFS. It can read data from HBase, Hive, Tachyon, Cassandra. It goes to an extent of integrating with Hive that Spark SQL basically any Hive query can run in Spark SQL. Okay, so the porting, if people have done a lot of code in case of Hive, they can directly use the same code in running for running it in Spark SQL. All right. So it can run on many kind of resource managers, and it can connect to many kind of data sources and read from them to an extent that it can read data from Cassandra. Right. So this diagram is clear to everyone. So Hiran's question is, can it read from S3 and relational databases? Yes, that's correct. It can read from S3 and also the relational databases. Tachyon is also a storage, Ishwar. All right. So Tachyon is kind of a memory-centric, reliable storage system. Okay, similar to HDFS. Can Spark read from middleware? It should be possible to read from middleware. Yes. Yes, definitely, Iswar. So it can read from Kafka, RabbitMQ. Yes. All right. That's how Spark streaming is done. All right. Iswar's question is, how about on HTTP endpoints? So in a very, the easier manner that the in case in case there is no data source existing for particular, there is no existing driver exist for a particular data source, then you can write your own driver. All right. Spark provides you the capability of writing your own driver which can connect to any kind of data source. All right. It does connect to the HTTP endpoints as well. You will see the how does it connect to Kafka, RabbitMQ, and HTTP endpoints when we discuss about Spark streaming. All right. Now that was about running Spark and reading data from various sources. Now what can you do? What meaningful things can you do on top of Spark? Okay, so you can run your queries in either the raw form of transformation and action similar to map and reduce, either in raw form, or you can query the data or churn the data in the form of SQL. Okay, you can churn the data in the form of SQL, like select star from this and group by. So because lot of work has been done in SQL, and it does make sense to provide an interface to the end user in the form of SQL. Okay, so you can churn lot of data using SQL. Using streaming, you can process a lot of data at a really fast speed if you use Spark streaming. Then MLlib, you can do the machine learning, as in train the machine to do a lot of magic for you using Spark. They have provided really great library. Unlike Mahat, they have provided a full framework for machine learning. Spark also provides you a great graph processing tool called GraphX. If you have to say build an algorithm which finds the page rank or which finds the common relations, then GraphX does a good job. Then Spark R. All right. So this diagram is clear to everyone. So Spark runs on these cluster managers and can read from many data sources and provides so many ways of processing the data. Now your question might be, then what's the point? Your question might be that can we write code directly in Spark Core? Yes. If we are not going to use SQL, streaming, MLlib, GraphX, or Spark R. All right. Good. Good. So everybody clear about various components in this? We will go into fair amount of depth into each of these components during the class. So, all right. Any questions still here? So John's question is there a programming paradigm to Spark Core? Yes. The way we had maps and reduces in case of in case of MapReduce, we have here something called transformation and actions. So there are so many functions which Spark Core provides you, and they can be categorized into two things. Those functions can be categorized into two buckets. One is called transformation and action. You will understand that as we go forward. So that's the paradigm we will be following, transformation and action. All right. Any other questions before we move forward? Ashish's question is, please explain one complete flow of data. Good, good point. Everybody okay with that question? All right. Should I go ahead with that? All right, great. All right, great, Ashish. Good question. So I'll just do a very brief way, and we will see that there are basically two kinds of data flows. Okay, two kinds of data flows. One comes under, the stream processing. Second comes under the normal analytics. Okay, analytics may be in the form of machine learning. It can be many forms. Okay, analytics is something which a generic term for various kinds of processing. Okay, now in case of stream processing, a lot of, I mean, the job is to process the data as and when the data comes in. Okay, so a streaming processing never stops. Okay, stream processing never stops. It keeps running, listening to Kafka or any other queue, maybe any other message queue, and keeps on reading data continuously. It never stops. It keeps reading data and it keeps processing data. That's a kind of stream processing. In case of stream processing, okay, we read the data, okay, push it to Spark dataset. All right, and then we will I have used the word data set. I have not used the correct word right now because that will again it would require a bit of time. So push it to Spark dataset, then run the run the transformations and actions, or maybe MLlib or graphics. All right, so or maybe SQL. So you will read the data. In case of stream processing, you will read the data continuously from the source, keep on pushing it to the Spark dataset. On the other hand, the transformations will keep on running on the dataset. Okay, so that's about processing. This is probably the most simple form I could come up with. With respect to the analytics, so the way it happens is you store huge data in HDFS, or maybe say Tachyon, or Cassandra. All right. Next is that load that data into Spark temporarily, or you can say that you have stored the data in HDFS, and now you write program to process the data on Spark. So this program, whatever you are going to do, this program which you are going to launch on your cluster, it is going to read data from HDFS, and this program could be using any of these libraries. Okay, either it would be like raw. Let's say you want to do a raw computation, you don't want to use any library, that you can do, or your program can use any of these libraries and process the data. Okay, we'll go into the details. All right, so Ashish's question is, we read data from maybe message queue from high input streams, as in such as Kafka, or maybe message queue. There are so many message queues. Okay, and so on. All right. At Amazon, we had our own SQS queue. Yes. So these points look similar to, yes, Storm, and that is where stream processing of Spark actually competes with Apache Storm. All right, Ishwar, you are right. It does compete with Storm. Now you read data from HDFS, load it into RAM of various machine, and then run your logic or run various libraries to reach to the results. Make sense to you? All right, all right. Hope this is clear to everyone. Sure, sure. We'll just let me just save it, and let me just save it. Okay. Good, good. All right, all right. So the Spark architecture, as we have talked about, is actually very comprehensive. The only part which Spark does not have is the storage. It does not have its own storage. All right. So, all right. Before we move forward for the detailed discussion on Spark architecture, do you want to take a break? Brilliant. We have a question from Sivram. It's a big question, so I'll just copy it here. All right, all right. Some of you have requested for 15 minutes break. So should we take a 15 minutes break? All right. Okay, 15 minutes break. Back by all right. I think I wrote PM instead of AM. Yeah, yeah, that's wrong. All right. Hello everyone, I'm back. Should we start now? Great, great. So everyone is back. Awesome. All right, good. All right, there was a question from someone and from Shivaram. So question was, I have a file called customers.csv. Size of the file is 3 gigabytes and I have 3 node Spark cluster where each node executor has one gigabyte. If I run the following code to find out, if I run the following code to find out number of lines in customers, does the Spark load data in memory for computation? If yes, how does the computation happens? All right, all right. So, okay. So, although we will cover this in detail in probably the second class, okay, second session, we'll go into the details exactly how do you run all of this. Okay, so I think although Mehdi has given a full code for this, okay, I'll park it till we understand RDD, because your question is how does the computation happens, right? So I'll park it till the point. Let's just finish understanding the basics, then it will make a lot of sense. We have to invariably go through the understanding of this example. All right, all right, let's say that this is 4 GB. Okay, so let's discuss it after this, after we understand the basics. Great, great, let's try to understand the basics. And thank you, uh, Mehdi, for sharing the code for this is brilliant. Yeah. All right. All right. So let's understand the heart of Spark architecture. The heart of Spark architecture, the backbone of Spark is the concept called RDD. Okay. So the concept called RDD is essentially a distributed data set on which e- either we can run actions or transformations. Okay, so let me first explain to you why does this representation of data matter so much. Okay, so any tool that is supposed to run any computing on data, remember that, is always this data oriented paradigm. Okay, let's take a case of R has something called data frame. So you in R you do all the operations on top of data frame. In Pig you have something called tuples and data sets, right? All the operations are always like first data set and then operation. Okay, so you always perform operations on data set. Now, if you see, there are other frameworks in the same manner which are supposed to do the processing of data. Let's take a case of SQL. SQL is also like very data oriented framework or the language. Okay, so in case of SQL, you also every query is has at least one table mentioned, right? There, all queries are oriented. Okay, are around the tables. So, okay, they have a concept called tables and rows and tables. I'll put it this way. All right. So no matter whenever you have to do a lot of data processing, the language is the oriented around the data set. So every query, every statement is around the data set. Okay, like for example, in case you take a language like Java or Python, okay, in those cases, these are like general languages, and don't don't really orient around data set. They can do anything not only related to the data set. So Python and Java, you can do things like for loop and all kinds of looping, and manipulating data is just one part. So if you look at the idea, these languages which are very data oriented, they are, every statement has data set in them. Therefore, it is actually possible to distribute their data and still keep the SQL same. Okay. While in case of Java and Python, since there could be a sequential input from the data, there could be a code which cannot be broken down in straight away into distributed computing. So all these systems like R, Pig, SQL, all of these have been transformed to Spark. So the basic idea about this newer form of computing, or let me also say that MapReduce. Okay, in case of MapReduce, every MapReduce has input data. Okay, although this input data folder, I would say, or file, can be small, but you you have to specify some folder or file. Here, in case of Java and Python, there is a representation called array for for your data, but this array is not really distributed. So this array is not something around which the whole language revolves. Okay, so it's just one small feature of the language. Therefore, these languages are more suitable, these paradigms are more suitable for any data oriented work. All right. So no matter what, in the history, whatever framework has been written to handle the data, small data or big, all of those start with the definition of the data. Okay. And in the same manner, the way Pig has data sets, in the same manner, we have RDD in case of Spark. It's a core concept. It's a core concept of an array, of a data table, of whatever you want to call it. So RDD is a distributed data set on which either we can run actions or transformations. All right. So the way it happens is you have got RDD, as in you have got, say, four nodes, one, two, three, four nodes, and uh, this single data set, this is, let's say, this is a single data set. Some of the elements, let's say this data set has 100 elements, so 25 elements will be on here, 25 will be here, 25 will be here, and 25 will be here. All right. So it's when you load data into RDD, it distributes data across multiple machines. Okay, you distribute data across multiple machines. Now after that you run transformation or action on that particular data. All right, so this RDD, what we call resilient distributed data set, it has got really good properties, as in that the if one machine goes down, the load shifts to another machine, so it is resilient. It can it can tolerate the failure of nodes. And resilient means it doesn't fail. It can recover from failures. Make sense to you? So this resilience distributed data set is, you can imagine that it's a big array of object, and each object can be anything. It can be a person, it can be customer, it can be plain text, it can be number, it can be another array. Okay, so if you have to represent a matrix, you can either represent it like a big array where each element is another array. So overall idea about RDD is the way you should think about it. Whenever you have big data and you want to churn it, you make you load that data in the form of RDD, in the form of an array of objects. Okay, let's say you are doing a file counting example. Now let me go back to what we were talking about here. Let's say we have customer.csv. It has got 4 GB, all right? And we are loading it on 3 nodes, okay? We are loading it on 3 nodes, okay? So the way it will be loaded, it would be loaded like we have, let me just try to form it. Let's say node 1, okay? We'll have line 1, line 2, up to say line 3, and up to line 100. All right, so that's a node 1. Node 1 is having this part of array. Node 2 will have out of this file, after 100, maybe up to 200. So I'm assuming there are 400 lines, all right, just for the convenience sake. Node 3. Is everybody with me, or should I explain the problem statement clearly? So basically we have to do a line count example in case of 4 gigabyte file using 3 nodes cluster. Yes, it is reliable to some extent, yes. All right. Now let's imagine that we have 200 to 300. So I'm assuming that there are 400 lines. Okay. So we have file of 4 gigabyte, and let's say 3 parts. Okay. It has 300 lines, for example. All right. And we have converted into 3 parts. Okay. So node 1, node 2, node 3 have this. Just give me a second. Let me try to make it look more sensible. All right. Is this clear how we have divided it? So if you have a file of say 4 GB, which is having say 300 lines, and you are loading it into Spark cluster, so it will be loaded like this: 1 to 100 on one node, 100 to 200 on another node, and so on. All right. Next phase would be now next phase would be doing the transformation. Okay, transformation, where we will convert each line into words. Okay, you will understand it again when we go into the details of it. Right now I'm not writing any code. Okay, so it will become like word 1, word 1, word 2, word 3, and so on. Okay, we'll convert each line into word by sending our code So we'll write our code and we'll send it to the node 1 and say execute this code on each object of the array, and that code will convert our line 1 into so many words. All right? And similarly we'll do here also. Okay, in the similar fashion we will do the things on this node as well. Okay, and once and whatever we are doing, we are it's happening. So when we are converting each line into words, that's happening for all the nodes. Okay, and afterwards we will run something like a group by. We will see group by, and that will aggregate the words. Okay, okay, so it'll generate the summation. So group by will first sort and then bring it together. All right, make sense to you, everyone? The next phase would be group by. Group by is a command, is a action provided by framework itself. All it does is sorts the data and groups, and and sorts the data and aggregates. That's a better word. And aggregate function, uh, you can provide the code, you can provide the code which can aggregate the data. All right, I think it's not very clear to everyone. Do not worry, in case it's not clear, it'll get clear as we go ahead into a detailed discussion. All right, so right now all I'm trying to show is that a big file broken down into lines, okay, into lines and represented as RDD, and the transformation, you see this funnel, it's basically a representation that transformation is happening on each node, and whenever required you can pull the data back to the driver where we started from. All right, Arvind, Ashish, Ishwar, George, Harsh, Hiran, Jitendra, John, Karthik, Mehdi, Shiv, and Vishwanath. So John, I was just asking if the RDD idea is clear. Yes, we can pull the data back to the driver whenever required. Yes, great, great. So everybody is with me. All right. So this is how we basically send transformations and actions to through Spark and get it done on RDD. And whenever required, we can save data back onto HDFS or bring the data to our Spark driver. So Jitan's question is, this is same as Hadoop. So what is the difference? The difference is that if you have to run multiple sets of transformation and action, you do not have to keep on loading again from MapReduce. Second difference is the MapReduce process is generally slow. These processes are far more faster. Okay, you will be able to compare it when I show you the execution at both on both the node on both MapReduce and Spark parallelly. Okay, S- so Ishwar's question is, will there be partitions? Yes, there'll be partitions of RDD. So partition 1, partition 2, partition 3, partition 4. All right, these are on different machines. Okay, I think I should just make a note here saying machine 1, machine 2, machine 3, machine 4. All right, Jiten? Good. Very good set of questions. All right. So a quick overview of other components in case of Spark. All right. So Spark SQL, which we will be covering in this course, runs on top of Apache Spark and has got a Hive compatibility and has got a huge performance and scalability because the way the way Spark SQL also works is the table on which it's operating is distributed across the cluster. So if you understand, if I explained correctly, so Spark SQL churns the big tables, any data in the form of tables, and you can continue using your Hive or standard SQL to churn the data. Say, finding the counts of words in a file, you can do it using Spark SQL as well. Okay? Other than writing the code in the native language, you will do it using the you can do it using the Spark SQL as well. All right? And okay, so most of the data churning, you will find very comfortable doing using Spark SQL. Spark SQL can be used to do usual transformations of the data in the form of SQL, joining the data, grouping the data, filtering the data, and all that can be done with Spark SQL very easily. Okay. Now the afterwards, once you have done the basic work using Spark SQL, you can proceed to other tools and use the same RDD, same table in others also. Okay, without reloading it. So on top of Spark SQL, so one use of Spark SQL is that you can mm, you can easily clean the data, or you can easily transform the data using Spark SQL. Other is that it provides you a server as well, so that you can connect from your BI tool. You can connect from BI tools such as BERT or maybe Talent or maybe some other tool like Microsoft reporting. You can connect from those tool to Spark SQL and represent the data in charts and whatever you want to do. That's another use of Spark SQL. Just like Hive server, Spark SQL also provides you a good server. Okay, and of course, Spark SQL provides you things like Spark UDF, as in user defined function. You can execute user defined function in Spark SQL. Similarly, the serializer, deserializer, in case your data is in some form which is not there as a standard SQL, you can load that using serializer Sardays. So which is like, for example, you are trying to load JSON data into SQL. You can use those Sardays, as in serializer, deserializer of JSON, to load the data. Okay. All right. Harsha's question is, if the file is loaded into RDD, what is the lifetime of the file and the table? Good question. All right. So question is, if a file is loaded, so lifetime is generally okay during the execution. That's all. Okay. But most important thing is it. can be retained retained in memory. I'll not use the persist word because Spark guys use persist word. Here I'm using uh, it can be retained in memory. So generally, whenever you are doing any processing work on top of Spark, it is only retained during the execution of the program, of your program, your job, your task, your console. If your console is connected, if you connected directly a console to Spark, it will remain connected, and as soon as you exit from the console, it will delete the data. Okay, good question. But you can retain, or as Spark guys say, that you can persist the data into the memory, into the RAM. You can tell Spark to keep your data into the RAM, not to free it, because Spark is anyway continuously running. Okay. Harsha's question is, if the file is sent back to HDFS, what is the difference between MapReduce and Spark? Okay. So we don't send the file to HDFS between every MapReduce cycle. If we start doing that, it'll become really, really slow. Okay. Good question. All right. Here, sending the file to HDFS is optional. In case of MapReduce, it is mandatory. So the way Hadoop or Hadoop MapReduce, the traditional MapReduce has been designed is to handle hundreds of petabyte data's processing, where we cannot retain 100 petabyte data into the memory. Okay, and that's the main thought behind the whole MapReduce. Okay, while Spark has been designed in it with the mindset that okay, you can handle hundreds of gigabytes data without any worry, but in case you are going for petabytes of data, you have to specifically mention that don't load the data completely. So Spark provides you far more control than the imposition. It doesn't impose. Mehdi's question is, persist file will delete if I exit from console. No. All right. Good. Good. Very good set of questions. Moving ahead. So, using Spark SQL, you can do analytics using your BI tool, representation of data, as well as you can execute your logic in the form of SQL and do a lot of data churning using SQL itself. So it's fairly stable and is working great. All right. Now, as we have already talked about, is is another problem called Spark Streaming. Spark Streaming is a small library. It's not a server. Spark Streaming is not a server. It's just a small library which keeps reading from various queues and pushing the data to the Spark RDD. So all the data which is anyway, streaming means we read the data from queues. Queues means continuous data. The lot of data keeps on coming continuously, and we keep on forming the windows out of it. And for each window, we run the program. For each window, we run the computation, and the results are displayed to the user or stored somewhere. Okay, so that's what is Spark streaming. Let's take a case of what I was doing at Amazon. So I think this will make more sense to you. All right, I think I should explain that one. That will give you, rather than only talking about only talking about Twitter. Let's talk about what I was doing at Amazon. So at Amazon, the image that you see here, okay, Amazon, let's say, we had this jeans, Amazon, okay, okay. So let's just take one particular jeans like this one. So you see this image on this side, all right? You see the image on the left hand side, and there are multiple images. Okay, so this is the page we owned. This is Amazon detail page. Although it's showing in, but it's a common code for everyone, whether in or US. All right. So here, if you see this one, this particular block, this image is being selected from the image is selected from around 10,000 images. Okay, why is 10,000 of images? Because there are hundreds of vendors, hundreds of sellers who are selling this particular jeans. Okay, generally that is the case. So there are hundreds of sellers, and all of them have periodically uploaded many kind of images. For some products there are more than 100 vendors. Okay, now we have to pick the image out of 10,000 images which is most suitable. Okay, so we wrote some algorithm. Okay, we run some complex algorithm. Okay, which compares all these 10,000 images with each other. So it's a heavy processing, it requires a heavy processing. Okay, which consumes okay, which is a complex algorithm. That's good enough. Image is selected from 10,000 of images, and now imagine the complexity. The change request the change request is coming from the user, from the sellers, continuously. There are a million products listed on Amazon. Now, you multiply the complexity. You have got for each product these many images, and then there are so many products listed on Amazon. And for them, there are so many, and for each of whenever, and these sellers are continuously updating the information. You'll be amazed at the rate at which they are updating the information. And every change request, even if you are changing the title of this page, okay, that impacts our display of the image. So based on many parameters, we were computing this image, which image need to be picked up, what size and all that. Okay, so based on various aspects, we were computing. So we basically blindly run the algorithm as soon as anything change on this particular product. Okay, so the problem statement is clear to everyone? No? Is the problem statement clear to everyone? So sellers are changing the products every now and then for all the products, and we are getting the changes. Okay, so in the form of queues, if we mark it like a SQS queue, we had something called SQS queue, similar to Kafka. Okay, okay, SQ contains the changes requested by sellers. All right, like this. So John is saying, where do these 10,000 images come from? These images are uploaded by various sellers over a long period of time. Yes, you are right, John. These are uploaded by sellers. All right. Is everyone with me, or have I completely lost you, or do I need to explain things? So all I'm explaining is a real case scenario where where we did a lot of stream processing. So changes are so there is a SQS queue. A queue is a big pipe of information where the data is continuously coming in and you are listening to it. Okay. Okay. Multiple machines, around 30 of those, around 30 machines. I'll just write 30 machines rather than multiple. All right. So 30 machines listens to the changes. Okay. So these 30 machines keep on reading the data from the queue and keep on processing it. And while processing, they basically what we did was we we read around 10 records, and we found that out of 10 records the change request is only one, meaning out of these 10 records there was only one change request for which the user has clicked save multiple times. When the user is clicking save multiple times, we are getting multiple change requests. Okay. Or they are just changing e and then as, and every time they're clicking on save. So we do the deduplication. Okay. We do the deduplication. So we read a lot of data from the queue, do the deduplication, then run the churning and save to the database. And these all 30 machines are listening to the SQL queue, SQS queue. Okay. So for that we did this stream processing. So we built a similar our own platform for this, but we could have ideally used uh, available platform which were there, like Storm or other systems. All right. So was I able to convey the problem statement? So now when we were running these 30 machines, we needed coordination amongst them, and there were various kinds of need that was required, as in sharing the data across these 30 machines and pushing the same code to all the 30 machines and so on. In case we are changing logic, then it was always a problem. All right. So there were many challenges when you try to run a program across multiple machines. Then there are many challenges. All right. So this kind of processing where we are continuously listening to the data, listening to the queue, meaning a program that never ends. Stream processing program never ends. So when you are writing such program, the strategy to do the testing is also different. As in, from left to right, if you have to stop the streaming process, you have to poison it. You put a poison on the left hand side, and then in your code you have to handle that poison. As in, when the request contains poison, then shut down the streaming. Okay. So streaming in itself is a good enough uh, good enough branch of the computing where, I mean, in the okay. All right. So in case of streaming, we read a lot of data which is coming for 1 millions of records. If there are thousands of records coming per second, what we do is we break down these thousands of records into big window and start doing the operation on the big windows. Okay. That way we convert lot of items into a small set of items. Okay. So okay. So Ishwar's point is I still did not get completely. All right. So if you have any doubts, specific doubts, I can clear it. If you have any specific doubt, I can clear it. All right, great, great. So this way, once we are done with the streaming, you save it. So we'll take a detailed example and we run it, run the Spark streaming, and try to demonstrate that one. All right. Now the next problem statement which Spark tries to solve is the machine learning. MLlib is a very good library. I have gone through both Mahout and MLlib, and I found MLlib to be very impressive, very impressive. So So basically, MLlib the objective of machine learning is programming computers to optimize the performance using example data or past experience. Okay, so basically, instead of you writing the code, let the computer understand by itself. It's a branch of artificial intelligence. It's designed the objective is to design and development of algorithm. Let the computer write the algorithm by itself. Okay, so basically computers evolve behavior based on the data. Okay, so although this machine learning has been going for quite some time, machine learning was not very successful for a couple of reasons so far. One, it was very theoretical so far, but now it has become really, really practical. Second, the data was not available earlier. That bigger data was not available, or you can say that people hadn't built the platforms which were people did not had not built the humongous data, because as I say that computers evolve behavior based on empirical data, which means the more the data, the better is the behavior. Okay, the more the data, the better is the behavior. Okay, if you have very small data, machine learning does not make any sense. If somebody comes up with an idea that he has 100 records or 500 records or 10,000 records and says that we can apply machine learning to figure out patterns and all of that, it doesn't make any sense. Okay, so for machine learning you should at least have something like 50,000 records, 100,000 records, or more than that. Otherwise most of the machine learning data becomes fairly useless. If you have thousands of record, it doesn't make much sense to have machine learning. All right, so now on one end machine learning demands more records, and Spark or these tools handle millions of records. Therefore, machine learning coupled with these tools which do the distributed computing solve a lot of problem. The day of supercomputers are no longer there. In case people are still buying supercomputers, it's mostly because of the PR. All right, it's a strong statement, but yeah, I'll stand by it. Okay, so basically, if you have to handle machine learning in today's time, you will have to use distributed computing, and MLlib is probably the best amongst all. All right, so we'll take one big example of machine learning during the course, and we'll go into the details of implementing one. All right, any questions at this point? All right, there are many applications of machine learning. You can generate recommendation of friends, dates, products to end user, classify. So the things like collaborative filtering or recommendation means collaborative filtering, and those things are also heavily assisted by machine learning algorithms. So automatically classify things into undefined groups as well as predefined groups. Undefined groups as in, given these emails, convert it into four buckets on any parameter you want. So this is classification without any defined goals. Or you could define that this means spam, that means non-spam, and therefore, given all of this data about spam and non-spam, do the classification of these emails. Okay, that's a kind of that's also a big machine learning application. So you must have seen Google already uses all of this. It uses all the information you provide to report a spam, and based on various machine learning algorithms, they figure out the pattern by itself. Okay, find similar content based on object properties. Okay, so that's another thing, as in, if you have to correlate the various newspapers, then you will be basically finding similar content amongst all the newspapers and aggregate them together. Identify key topics in a collection of text. As of today, the machine learning has also assisted natural language processing, meaning understanding natural language using the machine learning. As in, so either you can code yourself that this sentence means this means that, and we could write the grammar. But what people did was, let let machine learning assist NLP, natural language processing, so that this language processing, the English language processing or any other natural language processing, becomes really, really efficient. Okay, detect anomalies in the given data. If you have huge data and you have to find anomalies, as in something wrong, something which was not there earlier, so for that, machine learning algorithms do a very good job. Okay, ranking search results with user feedback learning. Okay, so uh, if you had noticed that if you start clicking a particular link in case of Google search results, that link keeps on coming up. Okay, so those kind of behaviors, there are lots of user behavior, such as stay how much time does the user stay on a particular URL, and so on. There are lots and lots of behaviors which search engines gather about the user so that they can improve their search results. Classifying DNA sequences, sentiment analysis, opinion mining, computer vision, and natural language processing, bioinformatics, speech and handwriting recognition. There are many, many uh, applications of machine learning. All right. So MLlib, which is a machine learning library of our Spark, is very easy to use. You can write your program either in Scala or Python or in Java. It is really high performance and has a high quality algorithms. Okay. So it has got high level APIs for machine learning pipelines. Okay, high level APIs, as in, it has provided something called Spark ML, which is a machine learning uh, markup language. Okay, which is a machine learning markup language, so that people don't have to keep writing code in order to do the machine learning. They can write in the markup language. It's similar, basically a XML kind of language. All right. Any questions on machine learning? So we'll go into a couple of examples end to end. We'll try to execute the predefined algorithms. We'll not be building new algorithms as part of this course, but we will be trying to use couple of algorithms. No questions? If you don't have questions, that means either I'm very bad or I'm very good. So I think it's the first one. Okay. I hope that everybody on the same page. So his first question is, do we learn basics of Python also? We will cover basics of Python in the course, no worries. Okay. But it's great if you put more efforts into learning at least one language. And we will also cover basics of Scala in this course. Okay. That should, because lots of people are inclined to learn Scala, and it sometimes makes sense to just because if you know any language, it's not a big deal to learn a new one. The objective is not to gain the mastery in the programming language. Instead, getting work done on Spark. All right. Great. Great. Any questions at this point? So we talked about many things today. We are just giving an overview of every topic. We'll go into the detailed examples as we go during the course. All right. We will dive deep into, first we'll start with transformations as we have given. Then we'll go first, before that we'll give you an overview of these languages, and then we will go in detailed into various tools, okay, such as Spark SQL, then MLlib, then GraphX, then Spark R, and so on. So be ready to learn many new things, okay, because when we talk about Spark R, I might have to give you a quick overview of how does R looks like. All right. So all right, great. Moving on. So now on the variety part, the complexity of algorithms part, graph algorithms are probably next to little less harder than the ML algorithms, but are still fairly difficult to get it right. Okay. Also, when I say complexity, complexity is always in terms of time consumed in doing the processing. So most of the algorithms of graph are number of if there is a graph which has got n number of nodes and m number of edges, the total processing time is generally n into m, total number of nodes multiplied by edges. That's a complexity of most of the problems in graph. The the uh, the tendency is to bring it down as much as we can, but in most of the graph algorithms we cannot bring it down. So there are two three kinds of complexity when we are talking about. One, in terms of algorithm, yes, programs are little complex to represent graph. Second second complexity is in terms of time complexity, time taken for the computer. All right. So a graph is basically lot of nodes connected by the edge. It's a concept. For example, when you are writing a complex XML which has internal references, that is also a graph. Okay. When you are building a crawler, building a crawler, y- that also is traversing a graph. Okay, it's a network of pages connected to each other. So as I said, nodes and edges, you can represent lots of problems in the form of nodes and edges. Okay, edge as in connecting line between the two nodes. So most of the problems can be actually converted into the graph problems. Okay, so there are many problems which are there that requires a lot of graph computation, such as finding common friends, finding, suggesting the friends, as well as figuring out the page rank of various people, various web pages. Okay, so for all those kind of processing, GraphX library does a very good job. So it is flexible in the sense that it can work with graphs and collections. It is really fast. It's comparable performance to the fastest specialized graph processing system, and is okay. The library of GraphX, because everything is open source, it's actually increasing at a very faster pace every day. Because if you subscribe to Spark's dev library, dev mailing list or user mailing list, you will find that there are the number of emails that come in are really high, and every day I see new graph algorithms from various people. Okay, each first question is, does Spark integrate with OrionDB or Neo4j? Let me check this one. I have not checked it yet. Let me check this one. All right. So GraphX algorithm, the few examples is PageRank. PageRank is, how many of you know what is PageRank algorithm? Anybody? Anyone? What is PageRank algorithm? Yes. I'll give you a hint. The company who is based on PageRank is ex CEO, has the same surname. Correct. It's Google. Okay, Ishwar is saying each web page will be ranked against some criteria. Correct. All right. All right. Anybody else? What is a page rank algorithm? The diagram on the right hand side would be more explanatory. Anyone? What does it mean by a page rank algorithm? All right. Good going, Ishwar. Ishwar says based on number of hits and type of the content. Okay. All right. So PageRank algorithm is the algorithm which made Google Google. Okay. Google became successful only because their PageRank algorithm. So as you can see the image here on the right hand side, you see a big face, a small face, and very small face. Okay, so those pages, these are pages, and the size of the sphere or the size of the circle represents how bigger the page, bigger the face. Okay, bigger the page rank, bigger the face. Okay, now you see these, basically those pages who are not referred by anybody, their page rank is lower. Those pages who are referred by nodes, and those nodes have more, those pages have more page rank, then you get more better page rank. Okay, PageRank is a measure of how many pages are referring to you, multiplied by what is their page rank. The people who are voting for you, the pages who are linking you, what is their page rank? If the pages who are linking you are having higher page rank, then you will get the higher page rank. Okay, so that's what is a page rank algorithm. All right, so such kind of algorithm though are very difficult to implement in single shot, and specifically on huge data. If you have billions of hundreds of billions of pages, then it's very difficult to form the page rank correctly. If you have a better page rank algorithm, you can still become the more successful company than Google. All right, therefore therefore these page rank algorithms are very important, though very popular, still difficult to implement. But good news is that you can directly use the PageRank algorithm as such. Let's say you are trying to do the same thing on Twitter. You are trying to compute something called Twitter PageRank. Okay, you want to compute Twitter PageRank. Then number of followers you can count, and if those followers have got good value, then you'll get a good value, and so on. So based on, if you have to, instead of you writing the PageRank algorithm, you can right away start using GraphX's PageRank algorithm. Next is the connected component algorithms. Connected components compute out of the nodes, out of a list of nodes, which nodes are well connected with each other. Out of all your friends, who all are connected well with each other. That's a figuring that out, like you can see here in this diagram. This section of the nodes are well connected with each other, while this section of nodes are well connected. So given a lot of points, you can always identify these are the connected components, these are not. Okay, the connected component idea is used in many places, be it displaying the recommendations of friends, uh, being it family of products, things are these things are bought together, and so on. Okay, so the connected components is a very popular concept. These are off the shelf algorithms available to you, so you will not be writing the program which will do the connected components. Instead, you will just use the library called connected components. Okay, also GraphX provides you the representation of a graph. You can write your own fresh algorithm using GraphX libraries. All right, triangle count, SVD++, and these all algorithms are available. Okay, all right, next point I wanted to discuss is that Spark R, which is R on Spark, it provides data frame like data frame in R, and lets you import data from R. It has rich operations such as group by, filter by, etc. as provided by R. It overcomes the memory limitations of R. Okay, it runs SQL query on R data frame. This is something very unique, which is not something you must have heard about. So R provides an idea of a data frame, and R also provides you things like filter by this, group by this, churn this data, and so on, intersect these two sets, and so on. Now Spark does a really clever thing. Spark provides you a way to run its SQL query on top of our data frame. Okay, because, and why is it able to do so? Because under the hood, R's data frame is represented as RDD. The data frame of R is represented as RDD. In case of SQL queries, the table which is going to churn is also an RDD, so it's able to provide you SQL queries on top of R. This is something really great. So if in an organization there is a person who is analyst and there is a person who is data scientist, so data scientist can prepare the data frame using R, and Analysts can churn the data using the SQL query and happily. So they don't have to worry about translating data or data imports. Yes, we are talking about Spark SQL only. That's correct, Iswar. Also, as I was telling you earlier, Spark R allows you using old R packages. In the world, R has got the highest number of packages with respect to the analytics as well as the machine learning. So R has got the highest number of packages, and Spark R allows to execute any of them on Spark R. All right, that's about the Spark R, and that's pretty much for today. All right. So do you have any questions before we move forward? Uh, Everyone? Probably we finished faster because you did not ask many questions. Any doubts about today's session? Okay, okay. So Jitan's question is how many hours every day? It will be 3 hours every day. How many days? It will be 11 days on every weekends. Two classes on every weekend. Right. For people who are from US, it'll be Friday and Saturday. Yeah. All right. There are a few questions. Let me copy them. So yeah, I'll answer this question. I'll have to check whether they have started supporting Neo4j and not. Okay. I'm not sure actually. Next is the question. So Harsha's question is knowing Python mandatory now during your sessions. It will be great, but we will cover Python. There are reasons why we are taking Python as sort of our main language. First, because it's easy to demo. It's quite easy to demo and easy to learn. Okay, and in case you, it's probably the easiest language to learn. In case you are coming from C, Java, or C++, or any other background, it will be quite fast for you. It'll come naturally to you. Okay, so even people who are working in Java, they themselves prefer Python when it comes to data churning. Okay, reason being there's a lot of libraries available in Python, as well as the when you churn a data you have to continuously inspect clean and so on, and that kind of job is well done using Python. Unlike, because here you have this command console where you can keep on trying things. Okay, similar to the same philosophy is also taken up by Spark, where you can directly connect to Spark using Python console, and you can keep on working from the console. Okay, and once you have done successfully, then you can write all those statements in a single file and then launch it like a script. So therefore, that is why we will prefer Python. Although there is Scala, we'll also give you an overview of Scala. Okay, we'll also give you an overview of Scala, but our main mode of communication will be Python. Also, we'll we'll have to give you a brief on R also when we'll discuss Spark R. Okay, but that's I mean the we objective is not to gain the expertise in these language. Objective is to understand what could be done in various kinds of scenarios. All right. All right. Yes, we will be sharing the videos. Okay, we'll be sharing the videos with you. The answer is yes. You will be able to pass the Spark certification without any other documentation outside this course. Yes, that's the effort which we are putting in. Okay, we have also worked hard on figuring out the course, but yes, if required, we will give you the references. Okay, if required, we'll give you the references in case you want to dig deeper. All right. Any other questions at this point? All right. All right. So feel free to have ask any questions. It's even if you have slightest doubt, maybe somebody else also is having the same doubt. Okay, so we should clear all those doubts immediately. And the sole objective of these sessions is having a very good discussion rather than having a one way communication. These sessions are not useful if you're not asking questions. All right. So I request all of you to keep asking questions. All right. Will you help us install Spark on my machine? So Jitendra, we will provide access to the cluster you must have already got, and from there you can start running. All right. John is saying let's have a look at the Spark sample code and running. All right. Let's just try to run it. All right. Right now. Okay, okay. So you are from this batch. Let me log into your account only. All right, here. All right. The only problem here is that we have only installed it on the first node. So these are the we are logging into the first node. Hadoop 1. From after logging into Hadoop 3, we are logging into Hadoop 1. Okay, because we'll install here also the client. So here you will see that there are okay PySpark. Also, we'll be replacing Spark with the latest version where you will see the R and everything. So we'll have to remove this older Spark and install new one. That we'll be doing over the week today, this week. All right. So this is the Python console of Spark. All right, John, is the font visible enough to everyone? So the way we did was we first logged in into Hadoop 1 from the browser, it, from the browser we could only log into Hadoop 3. So we logged in into Hadoop 1, and then we executed PySpark. Okay. User lib spark bin PySpark. All right. So, Jitendra, are you able to log in into your console and see this page? Yeah. All right. So this is the console. This is the console. All right. And here, from here, you can write your program as okay. So let's say you loaded lines as so here. This is the Python console. You can load data from HDFS in this manner, and you can upload this data using the hue window. Where is the hue window? Here is the hue window. Okay. All right. Let's just upload some text file. All right. I'm just uploading on my HDFS. So you can also do the same thing. Where can I find some big.txt? Big.txt. All right. So here you can load the data using Spark console, saying user spark1. Spark1 is your login, and say big.txt. We are loading the data, and we can give this name. So what are we doing exactly? sc.text file, not text file. Okay. sc.text file loads the file from text file from any place. Here we are loading from HDFS, and this file big.txt we just uploaded to HDFS using this Hue browser. Okay. So RDD is our data. Let's try to take 10 records out of this full big RDD. Let's see what happens. So it is giving us these 10 lines. Do you see that? Okay. The login password is available here. You can see Jitender here. In the LMS page. If you have registered, you will be able to see this. All right. Now this RDD, this is our RDD on which we have loaded the data. Upon this RDD, we can do any operation we want. Okay. Any operation we want. So we will go into the details of how to do the operations, how to do in the details, how to run a word count on this. Let's say we want to split the data into the parts. Okay, so we could do rdd1 equals to rdd. Don't worry, in case you are not able to uh, get it right now. You will get it as we go forward. Okay, so we define our method called split, and whatever string it is, so it will do is string dot split, and that's it. So we just defined a method called splt, which can split the data like we are trying to test it on Sandeep Giri. So it's splt. Oh, it's not returning actually. We were supposed to return the value. Define this. All right. So we are just trying to write a small function in Python called splt. What it does is it returns the data split it based on space. So if I say Sandeep space Giri, it will be splitting into an array. Now we'll send the same thing to the we'll we'll send the same thing to the RDD. We'll say RDD1. This is a new RDD we are creating after we are running this method called split on all the nodes using flat map. So RDD1, if we say take 10, it will show us the 10 words. Do you see that? So we have broken our RDD earlier. In our RDD, each object was a line. Now, newer RDD called RDD1 has each object as the word. All right. So this was a little hands-on, John. So did it make sense to you?